All right, in this video, we'll take a look at motion graphs. And there are two types. Two types of motion graph are distance time and speed time. Both graphs will have time on the x-axis. It's a general rule of thumb, whenever time is one of your two variables, you stick it on the x-axis because the vast majority of time is the independent variable. What makes them different is the label that we put on the y. In the distance time graph, it's distance on the y-axis. In the speed time graph, it's speed on the y-axis. So we get time on the x, distance on the y for this distance time, and again, time on the x in both cases, or speed on the y for the speed time graphs. Distance time graphs are also referred to as speed graphs. And yeah, I know it seems contradictory because this is a speed time graph down here. But if we look at the two variables that are on the axis, they are the two variables that go into calculating the speed of an object. And if we were to calculate the slope of a line on a distance time graph, we would be calculating the speed of the object, because it's rise over run, distance over time. The speed time graph would be some kind of change in speed over time. Change in speed or velocity over time is acceleration. So a speed time graph is often referred to as an acceleration graph. So distance time graphs, distance on the y, time on the x, are often referred to as speed graphs because the slope of the line that you calculate there would be the speed of the object, rise over run, change in y over change in x. It would be distance divided by time, the speed equation. And then speed time graphs, speed on the y, time on the x, are sometimes referred to as acceleration graphs because when you do slope, rise over run, change in y over change in x, it's change in speed over change in time, which is basically the acceleration equation. Now, we will look at the mathematical interpretation, being able to take these graphs, calculate slopes, get the actual speeds, get the actual accelerations of the object from the graph. But we're going to start with just general interpretation, looking at what the lines mean on each type of graph and what they tell us about the motion of the object, and learning to equate one with the other, what the comparable speed or acceleration graph would look like for each individual object. Let's do it this way. So I'll draw the distance time ones over here, and I'll draw speed time over here. First thing I want to do is just learn how to interpret some basic shapes and what these shapes mean on the two different graphs. And the first basic shape is going to be a horizontal line, and understanding what the horizontal line means on each of these two graphs. Whenever confronted with the horizontal line, the first thing you should do is look over at the y-axis, because whatever's not changing here is whatever is on the y-axis. So on the distance time graph, when we see that horizontal line, what's not changing is distance. So what that means is the object is not moving. Again, a horizontal line on the distance time graph, you come over to the y-axis to see what's not changing. What's not changing is distance. The object isn't getting any closer. It isn't getting any further away. So our only assumption can be that the object is not moving. The horizontal line on the speed time graph is interpreted differently because of what's on the y-axis. It's speed on the y-axis. So speed is not changing on this graph. This is something moving at a constant speed. Or velocity. You could put v over here instead of s. I'm moving at a constant velocity if you want to make it a velocity time graph. So that's your horizontal line. That's how you interpret a horizontal line on both graphs. Quite different because of the labeling on the y-axis. Next shape that I want to be able to interpret is a straight line going up. Straight line going up, again, on both graphs will have a very different interpretation. We know something's increasing and something is increasing in a linear fashion. Something has a constant increase to it. And again, it's what's on this axis that's going to determine what's going on here. So our distance is increasing in a linear fashion. It's moving away at a constant rate. Another way of saying that is that it's moving away with a constant speed. Again, as I mentioned before on the previous slide, when we talk about distance time graph and we do the slopes of the line on a distance time graph, what we'd be calculating is the speed of the object because it's rise over run, it's distance over time. A straight line has a constant slope. Therefore, a straight line has a constant speed on a distance time graph. Over on the speed time graph, again, it's a linear increase. Something is increasing at a constant rate. The question then becomes, what is increasing? We look to the y-axis and we see speed is increasing at a constant rate. So this is an object that has a constant acceleration, more so because calculating the slope here is delta y over delta x. Vf would be a larger number than Vi. This is constant positive acceleration. It's speeding up at a constant rate. Again, speed is increasing, that's positive acceleration. If we think about it in context of slope, our change in y is our ending position on the y-axis minus our starting position on the y-axis. So this number up here minus this number down here, big number minus small number, positive number, positive acceleration. This is an object that is undergoing constant positive acceleration. We want to be able to interpret the opposite kind of line, which would be a straight line going up. And again, it's going to have a different meaning depending on what kind of graph we're looking at. It's a linear decrease in distance here. So the object is getting closer. This object is getting closer and the line is straight, meaning it's getting closer at a constant rate or constant speed. It's moving back towards its starting position at a constant speed. And again, we think about this line in terms of slope, rise over run. Slope is speed on this graph. The slope is constant, so my speed is constant. So when you see a line going down on a distance time graph, that is an object getting closer at a constant speed. On this one, it's speed that's decreasing, so our interpretation is different. It's a straight line again. So we know the rate is constant, the acceleration is constant. This time this would be negative acceleration. There's two ways we know that's negative acceleration. One, the speed is decreasing. We're starting at a higher speed, going to a lower speed. Whenever the speed is decreasing, that is a negative acceleration. And then the other way we know is the slope part. Because the slope is constant, the acceleration is constant, because slope is acceleration on this graph. So this is constant negative acceleration. So those are your three possible straight lines that you would get on these graphs. The other possibility is a curved line on either one of these graphs. And understanding the meaning of a curved line is all about understanding the slope thing. On a distance-time graph, slope is speed. So down here at the bottom of my graph, I have a slope that's kind of like that. Up here, I have a slope that's kind of like that. I am going from a lower slope to a higher slope, which means I'm going from a lower speed to a higher speed. This is an object that is speeding up as it moves away. Remember, we can say speeding up is positive acceleration. So it's positive acceleration. Again, the line is going up, so the distance is increasing. So this is moving away as it speeds up. We have the same kind of thing over here. It's a low slope down here. It's a higher slope up there. So my slope is increasing, but what's on this graph is speed. Well, not speed, acceleration. Low acceleration here, high acceleration up there. The acceleration is increasing. So it's accelerating, it's positive acceleration because the slopes here would be positive. So we can say it's a rate of positive acceleration if we want to. Line going up is positive. But that rate of acceleration is changing. It's starting off with a low acceleration, then it's picking up acceleration as it goes, going faster and faster and faster. The opposite kind of curve obviously gives us the opposite kind of information. So on this graph, I'm starting off at a higher slope, but I'm ending at a lower slope. And again, on the distance time graph, slope is speed. So I'm starting off at a high speed, going to a lower speed, I'm slowing down. So this would be negative acceleration. So slowing down, negative acceleration. And again, the line is going up, so this object is moving away. On the distance time graph, when the line is going up, the object is moving away. When the line is going down, the object is getting closer. Again, over here, high slope to lower slope. My slope is decreasing, but on the speed time graph or velocity time graph, this is acceleration that we're looking at. So my rate of acceleration is decreasing. The line is going up, so it is still positive acceleration. The speed is still increasing as it goes, so it would be positive. But the rate of acceleration is decreasing. And again, both those curves can be done the other way around. We could have the object moving closer here, or we could be talking about negative acceleration over there. What it comes down to is to this. the distance time graph, straight lines mean constant speed. On the speed time or velocity time graph, straight lines mean constant acceleration. On the distance time graph, curved lines mean the object is accelerating. Either speeding up or slowing down depending on how the slope changes. So again, look to see what's happening to the slope. If it's getting steeper, then you're increasing its speed, that's positive acceleration. If your line is getting lower slope or flatter, then you've got negative acceleration, it's slowing down. Over here, curved lines mean the rate of acceleration is changing. Again, slopes over here are speed. When this line curves, speed is changing. The object is accelerating. Over here, curved lines means the acceleration is changing. It's accelerating, but it's changing its rate of acceleration. Over here, horizontal line. Means it's not moving. Distance isn't changing. So again, we interpret that as not moving. Over here, horizontal. It means it's not accelerating. So speed or velocity is constant. So there's no acceleration. Over here, slope is speed. Over here, slope is acceleration. So again, some of the things you need to know, some of the things you need to understand. Up and down, depending on that. On the distance time, up means moving away. Down means moving closer. Can't forget that. Up means moving away, down means moving closer. Over here, up means positive acceleration. Down means negative. So again, those are little bits and pieces. That's kind of a summary of everything that I mentioned and everything that you need to know about interpreting these graphs, just looking at the shapes, just looking at what the shapes are telling you. So you can expect to see questions where you're just interpreting shapes. So I'll give you a graph. Won't really tell you much more about it, just give you a graph. And I'll put a line on it. And you'll have options that you're going to choose from that describe what's going on in this particular graph. First thing I'm going to do is figure out what type of graph it is. Because there's speed over here on the y-axis, and again, that could be velocity. I'm tailoring this towards the practice that I'm giving you. In the practice I'm giving you, it's speed that's over there on the y-axis. Sometimes it's velocity. It's still interpreted the same way. Because it's speed or velocity over here, I know it's an acceleration graph. And so I start thinking about all the things that I know about acceleration graphs, like the straight line. The straight line on an acceleration graph means constant acceleration. And again, I know it's got constant acceleration because the line's straight. The second thing that I then interpret is the direction, up or down. And this line is going down. That tells me it's negative acceleration. Or that it's slowing down. And I would look for the answer option that matched that. That said something about the acceleration being constant, said something about it being negative or slowing down. That's how I would choose my answer on that. If I change that y-axis to d, then the whole interpretation changes. So again, you've got to look over here and you've got to see what that y-axis says before you can make any decisions. Final thing I want to talk about is doing the actual math that goes along with this. So I put some numbers and I put some units over here on my axes. Let me move this a little bit, make it easier to see. So still dealing with speed over here. I'm going to say my speeds are in meters per second. Still dealing with time over here. I'm going to say my times are in second. If the question were to ask you, what is the acceleration of this object? Then what you're going to do is calculate the slope of that line. And slope, as you should already know, is change in y over change in x. Or yf minus yi over xf minus xi. On my y-axis, I'm starting off at 10, and I'm ending down here, which I'm going to estimate is about 1. This line does not go all the way to the y-axis. It ends about right here. So I'm going to interpret that as 1, 2, 3, 4. It's about 1. So my change in y is going to be 10 minus 1. Or the other way around. 1 minus 10, almost messed that up. It's f minus I. So 1 minus 10. And that's meters per second. And my change in x, I'm starting off at 0 and I'm ending at 15. So f minus I, 15 minus 0. And that's in seconds. So this is negative 9 meters per second over 15 seconds. 9 divided by 15 gives us the magnitude. And negative 9 divided by 15 gives us the magnitude, which is negative 0.6. And that negative, again, we should expect because this was negative acceleration, slowing down. And the unit is just what we have here, meters per second, or meters per second squared. Because these two time units are the same, we can square those. Talk about meters per second instead. So again, you calculate the slopes of the line to figure out what the actual accelerations are, what the actual speeds are for your particular object. Now, what does it mean if you calculate a negative speed? Well, that's just that directional information. You're really looking at velocity. And that negative is just telling you that it's moving back towards its starting position. It's giving you the directional part. So again, when we talk about these graphs, distance time graphs as being a speed graph, well, if you're dealing with positives and negatives, you really are looking at velocity. So you could call it a velocity graph. And same thing over here. We get positives and negatives with the speed time graphs. Again, the positives and negatives are really just telling us directions.